Hi friends, in the last chapter we learnt all about motion and the different physics terms like distance, displacement, speed and velocity. But what causes motion? For example, if I take this ball, what do I need to do to give motion to the ball? That's right, I need to give it a push. So I need to apply a force on the ball to give it motion. And what is needed to stop the motion of the ball? Again, a force. Similarly, if you consider the motion of a car, it's the engine that applies the force on the car, causing it to move. And the brakes apply a force to stop the car. And force is going to be the topic of this video. We're going to learn all about force, the different types of force, and the effects of force. I'm going to make the concepts really easy for you. And after you watch this video, do try solving the quiz and the top 3 questions on this topic. Links are given below the video. I'm sure you know what force is. But in physics, how can we define force? There's a very simple definition in physics. Force is defined as a push or a pull. For example, to move this ball, I need to give it a push. So the force here is a push. And when the ball is moving, I need to apply a push to stop the ball. And to move this toy, I need to pull it. So here the force is a pull on the toy. As we discussed, in physics, force is defined as a push or a pull. Now let me ask you, is force a scalar quantity or a vector quantity? That's right, force is a vector quantity. Remember, scalar quantities only have magnitude. They only have a value, but no direction. Vector quantities have both magnitude and direction. And if you think about force, it makes sense because when we apply a force, there's a magnitude as well as a direction. Or for example, when I pull this toy, let's say with a 1 Newton force, 1 Newton is the magnitude and the direction represented by the arrow here is along the string. Forces can be divided into 2 types, force at contact and force at a distance. In force at contact, there is a real contact when the force is applied. For example, when I push this ball, can you see that there's a real contact between my hand and the ball? Or when I pull this toy with the string, there's a contact with my hand and the string. So in force of contact, there's a real contact. But in force at a distance, contact is not necessary. For example, if I lift this ball and I drop it, how does the ball fall? That's right, due to the gravitational force on the ball. And gravitational force acts at a distance. There is no real contact here. Now, is magnetic force force at a distance? That's right. Magnetic force is force at a distance. As you can see here, when I bring the magnet near the pin, it can attract the pin from a distance. So contact is not necessary. And just like gravitational force, magnetic force is also force at a distance. Another example of force at a distance is electrostatic force, the force between charges. We know that like charges, they repel each other, and unlike charges, attract each other. But contact is not necessary. It's force at a distance. For example, the pull between protons and electrons in an atom is electrostatic force, force at a distance. So we looked at 2 types of forces, force at contact and force at a distance. Examples of force at contact was when I push the ball, so there's a contact, or when I pull this toy, or when a boxer punches his opponent, that's force at contact. And what are the examples of force at a distance? Gravitational force, the force between the earth and the ball, or the magnetic force, when the magnet pulls this pin. And as we discussed, electrostatic force. These are forces at a distance where contact is not necessary. Let's place the definition of force and two types of forces, force at contact and force at a distance, on our concept board. What are the effects of force? Force has many different effects. So we are going to divide it into 5 points. Let's start with the first one. Force can set a stationary object into motion. For example, this ball is stationary, and if I apply a force, I can set it into motion. The second effect of force is it can stop a moving object. For example, if this ball is in motion, I apply a force and I can stop it. The third effect of force is it can change the speed of a moving body. For example, if this ball is moving with a slow speed and I hit it, I can increase the speed of the ball. The fourth effect of force is it can change the direction of a moving body. For example, if the ball is moving like this and I apply a force, I can change the direction of the ball. Or if you played cricket or baseball, you know that when you hit the ball, you can change the speed and the direction of the ball. The fifth effect of force is it can change the dimensions of a body. For example, if I squeeze this soft ball, I can change its shape. Or if I take this spring here and if I compress it, you can see I can change the shape of the spring. Or if I stretch it, the shape changes. So these are the 5 different effects of force. As we discussed, the simple definition of force is a push or a pull. A more fancy definition of force is a physical quantity that changes or tends to change the state of rest or motion of a body, or changes the dimensions of a body. Now let's understand this definition. What does physical quantity mean? Physical quantity is something that can be measured. For example, we can say the force is 5 Newton. So it has a value and the unit is Newton. And as we saw, when we apply a force, we can change the state of rest of this ball, or I can change the state of motion. So when the ball is moving, I stop the ball. Or when we apply a force, we can change the dimensions of this ball. So we can change the shape. Let's pin the different effects of force and this new definition of force on our concept board. Now, what do you think happens when multiple forces act on a body? As we saw, a single force can make the body move. So when I pull this toy. But now if I apply 2 forces, one with this string and one with this white string. Now the 2 forces, if they are equal and opposite, as you can see, the toy does not move, because these 2 forces are cancelling each other. These are called balanced forces, and the net force here is 0. Now if I pull the toy like this with the 2 strings in the same direction, so can you see that multiple forces are acting on the toy, one with the red string and one with the white string. And these forces, they don't cancel each other. They are called unbalanced forces because the net force here was not 0. And the unbalanced forces is needed to set a stationary object into motion. Or as we saw, it can be used to stop a moving object, or change the speed of a moving body, or change the direction of a moving body. Balanced forces can change the shape of a body. For example, if I squeeze this ball, the balanced forces here are acting from this part of my hand, so these fingers, and this part of my hand. So the 2 forces cancel each other. The ball is not going anywhere, but its shape, its dimension is changing. Another example is using a spring. So when I compress this spring, I am applying an equal and opposite force on either side. And as you can see, these 2 balanced forces are compressing the spring. They are changing the shape of the spring. And now when I stretch the spring, these two balanced forces are increasing the length of the spring. We know that unbalanced force is needed to start the motion of a body. For example, when I apply a force on this ball, I set it into motion. Now what happens when the force is removed? Will the ball continue in its state of motion forever? Let's say this table is very long. So will the ball keep on moving forever? We know from our experience that's not true. The ball will finally go and stop at a point. Now why does the ball stop? That's right, it's due to friction. There's a frictional force acting on the ball all the time, opposing the motion of the ball. And it is this unbalanced force that stops the ball. But let's say this table was frictionless. Then what will happen? This ball will continue in motion forever because there's no unbalanced force to stop the motion of the ball. Now what are some other examples where friction stops the motion? When you kick a football on a field, the football finally stops due to the friction of the grass on the ball. Or let's say a car is going on a road and the driver is not pressing the accelerator or brake when the car is in motion, but the car will finally stop even without the brakes. It's due to the friction of the road on the wheels. Or let's say you're pedaling a bicycle and you stop pedaling. The bicycle finally stops due to friction. So it is this unbalanced force that stops the motion of these bodies. As we saw, when one force or more than one force acts on a body and we analyze the forces, then we can say the forces on the body are balanced forces or they are unbalanced forces. Now in the case of balanced forces, the net force is zero. So the body is in a state of rest or it's in uniform motion. Uniform motion means the body is moving with a constant velocity, and this happens when there are balanced forces. The net or resultant force is zero. Now if you think about unbalanced forces, the net force is not zero. So the body is in a state of non-uniform motion. Here the velocity of the body is increasing or decreasing. This means the body is under acceleration or retardation when unbalanced forces are applied on the body because the net force is not zero. Do you know how force is measured? Remember, force is a vector quantity, so it has both magnitude and direction. The SI unit used to measure magnitude is Newton, denoted by capital N. Now what instrument is used to measure the magnitude of a force? Let me give you a hint. Weight is a type of force. Weight is a force due to Earth's pull on an object, and the direction of weight is always downwards. But what instrument is used to measure weight? That's right, it's a spring balance. And let me show you a spring balance here. And as you can see, it is used to measure the weight of this ball. The reading is 2 Newton. As we saw, we can use a spring balance to measure the weight of a body. But now how can we use the spring balance to measure force? Let me show you. Let's say we place the ball like this, connected to the spring balance. What will be the reading of the spring balance here? That's right, it's going to be 0 because the entire weight of the ball is acting on the table and the spring is not being pulled. Now let's say I want to measure the force with which I pull the ball. But rather than pulling it from the string here, I'm going to pull it using the spring balance. So when I pull the ball like this, the reading on the spring balance will give me the force with which I'm pulling the ball. And you can try this yourself. Take the spring balance and try to pull a heavier object like a chair with the spring balance. Then when you look at the reading on the spring balance while you're pulling the chair, that's the value of the force. So the spring balance will help you measure the force with which you're pulling the chair. As we discussed, force is measured in the unit Newton. Newton is the SI unit of force. Now to understand the unit Newton, we need to look at the formula for force. We know from our experience that a small force causes a small increase in speed, but a large force causes a greater increase in speed. There's more acceleration here. And this is exactly what Newton's second law of motion states, that the rate of change of linear momentum of a body is directly proportional to the applied force, and it takes place in the direction of the force. Let's analyze Newton's second law and derive the formula for force. Now, do you know what is momentum? Momentum is mass into velocity. So P equals m into v, where P is the symbol of momentum. For this ball, the momentum is going to be the mass of the ball multiplied by the velocity of the ball. When we say linear momentum, we mean the body is traveling in a straight line, like here. And change of linear momentum means final momentum minus the initial momentum. Now, final momentum will be m into v, where v is the final velocity. And the initial momentum will be m into u, where u is the initial velocity. So, change of linear momentum is mv minus mu. And what will be the rate of change of linear momentum? That's right, mv minus mu by t. For rate, we need to divide by time. Here t is the time. And according to the second law, it states that the force applied on a body is directly proportional to the rate of change of linear momentum of the body. So F is directly proportional to mv minus mu by t. Now if you take m common, we have v minus u by t. And what is v minus u by t? That's right, acceleration. So F, the force, is directly proportional to mass into acceleration. Now if we want to change this directly proportional relation into an equation, we need to use a constant of proportionality. So we have F equal to K into ma. K is the constant of proportionality here. And based on the units, the scientists set it to be 1. So the equation becomes F equal to ma. The force on a body, so the force applied on a body is the mass of the body into the acceleration of the body. And that's our formula for force, F equal to ma. How can we define 1 Newton based on the formula F equal to ma? It's really easy. If you look at the formula F equal to ma, so 1 Newton is the force that needs to be applied on a body of mass 1 kg to give it an acceleration of 1 meter per second square. So 1 Newton equals 1 kg into 1 meter per second square. Or the unit Newton is basically kg into meter per second square. Now if I ask you how much force needs to be applied on a body of mass 3 kg to give it an acceleration of 2 meter per second square. That's right, the force is equal to 6 Newton. You just have to use the formula F equal to ma. And if you substitute the values 3 kg and 2 meter per second square and just multiply them, you get the force as 6 Newton. Let's say a force of 20 Newton is applied on a body of mass 5 kg. What is the acceleration here? That's right, the acceleration is going to be 4 meter per second square. We can use the formula F equal to ma. Now if we bring the acceleration a on the left hand side, we get a equal to force by mass. And substituting the values, the acceleration is 4 meter per second square. As we discussed, the SI unit of force is Newton. And did you know that the CGS unit of force is dyne? As we saw, 1 Newton equals 1 kg into 1 meter per second square. And similarly in the CGS system, 1 dyne equals 1 gram into 1 centimeter per second square. So in CGS we use grams and centimeters. Now let me ask you, 1 Newton is how many dyne? What is this unit conversion? That's right. 1 Newton equals 10 to the power 5 dyne. So that's 100,000 dyne or 1 lakh dyne. Now how do we get this unit conversion? So it's pretty simple. You start with 1 Newton equals 1 kg into 1 meter per second square. Now since we want to convert to the CGS units, we need to convert 1 kg to grams. So that's 1000 grams. And 1 meter per second square is going to be 100 centimeter per second square. So if you multiply those numbers, you're going to get 10 to the power 5. 10 to the power 5 grams centimeter per second square. So that's basically 10 to the power 5 dyne. 100,000 dyne. Let's place the important formula of force F equal to ma and the unit of force on our concept board. Friends, I hope the concept of force is crystal clear to you now. So now I don't have to force you to try the quiz and the top 3 questions for this video. Links are given below. And do remember to like, comment and share out this video. And if you haven't subscribed to my YouTube channel already, hit the subscribe button right now. You can check my Facebook page and do check out my website manochaacademy.com. I'll put the links below. Thanks for watching.